Hi everyone, welcome to Design for Success with Amazon Elasticache Best Practices. My name is Damon LaKyle, and I am delighted to be here with you for this session. I'm a solutions architect focused on in-memory data stores in Amazon Elasticache. Now in this session, we'll first talk about the modern application requirements. And we'll focus on three of those different requirements, the first of which is scalability. Now, scalability is the ability to scale out your supporting architecture, and it allows us to scale up or scale out, or when the time is right, scale back in or scale back down when it makes sense. Now, high availability is the next topic, and that provides us the ability to have high availability through data replication. And that's how we can use multiple availability zones with automatic failover in Redis. And then we'll talk about security. And since I placed it kind of towards the end of the session, hopefully it will stay in your head the longest because it's very, very important. And then I've got a few resources links, and we'll talk about those towards the end. So modern application requirements, it's quite a bit different than it was like 10 years ago, right? So as applications have evolved and grown and they really increase in complexity and size, there's really this constant and increasing need for performance and scale and availability. And that in turn puts pressure on our supporting architecture. And those demands from these modern applications really only have one direction, and that's up, right? So applications are evolving really from these monolithic kind of single server applications that maybe support thousands of users. And now we've grown to communities of global users and microservices and IoT devices, right? And these users and services and devices, they're all sending millions of requests per second across the globe. And of course, they all demand an immediate response. And these are the kinds of changes that have driven application developers to kind of rethink how application data is stored and accessed. Now, modern applications support millions of users. They operate on a global scale, and the number of requests really sometimes is just simply mind-boggling. Some of our customers, in fact, don't measure latency in milliseconds now, but microseconds. So, and to be clear, that's 1 million microseconds in a single second. So the demands on modern applications really is truly unprecedented. And we're seeing this across all of our customers' verticals, actually. Imagine maybe a massive online game tracking the status of millions of players. Maybe you're processing data in real time from social media feeds, millions of feeds. Or take maybe real-time bidding where the delay of a few hundred microseconds can impact the value of that service. And that's where Amazon Elasticache has a meaningful impact for our customers, when there is really just this absolute need for speed. So Amazon Elasticache is an in-memory data store and cache, and it is highly scalable, allowing for Redis nodes from as small as 1 node to as large as 500 in a cluster. And with this non-disruptive horizontal scaling we have, it can scale to kind of meet the challenging and changing needs of your applications that we just talked about. And extreme performance is what Amazon Elasticache is really well known for. As an example, Elasticache can execute some commands in about 10 microseconds. And combined with that horizontal scaling, this provides the ability to have tens of millions of requests per second. And we know you have really important projects to work on, more than just this backend stuff that's core to your business. And that's why Amazon Elasticache is a fully managed service. So you can really focus more on those important things that you're working on. We'll provision the hardware, we'll install the software, we'll configure the engine with best practices, we'll monitor important cluster metrics in CloudWatch, and then we'll help you easily set up secure and encrypted backups as well. And since Elasticache is fully compatible with both Redis and Memcached engines, you can move your existing workloads into Amazon Elasticache with little or even no code changes. So let's talk about the different ways that Amazon Elasticache can scale to meet your needs. So this is going to be a simple example of how Elasticache for Redis scales for read capacity. Let's say we have our clients that are running on Amazon EC2 or maybe in AWS Lambda functions. And they're going to be writing and reading to the network, of course. And their writes and updates are being sent to what we call the Elasticache for Redis primary node. And their reads could too, of course, but the primary node can then in turn replicate its data to up to 5 read replica nodes. And here, of course, we only see 2. And these read replica nodes then allow an increase in read capacity for your clients. They also provide the ability to fail over to one of them should something happen to that primary node. And we'll talk about failover a little bit later. Now, this is the basic unit of a cluster, and it's called a replication group. Sometimes it's referred to as a shard as well, and here we have a primary node, which is responsible for all of our writes, and from 1 to 5 optional read replica nodes. A few things to keep in mind here, right, is as you increase the number of read replicas, it's going to add some additional load to your CPU. It's also going to need some of the primary node network capacity because it has to replicate its data to those extra nodes. But the flip side of that is the more replicas you have, the more bandwidth you have for those read-heavy workloads. And that leaves the primary node more capacity to accept writes and updates. And another advantage of having 2 or more replicas instead of just 1 is that if we experience a primary node failure, it has a faster failover time than having just 1 replica. And it's because we have a majority of nodes that can agree on which replica is the new primary, which is a really fast decision. It takes a little bit longer if you don't have a majority of nodes. So remember that to scale a read-heavy workload, you should consider adding read replicas, and you can adjust the number of replicas while your cluster is online, so you don't have to think that this is some kind of static configuration. So what you see here can be thought of as a cluster mode disabled cluster, where you only ever have a single primary with its own replicas, but it can also be viewed as a cluster mode enabled cluster with just a single shard. But in this situation, we can add shards whenever we want, which is what we're going to talk about next. So if you have cluster mode enabled, which means it uses the Redis cluster protocol, then you have the ability to scale horizontally by adding more shards. Now, this means we distribute our data across multiple shards. Each shard handles a subset of our total data set so that collectively, this cluster has more resources and it can respond faster. Now, scaling horizontally is cost effective because you're scaling incrementally, right? Maybe just a shard at a time or multiple shards at once. It doesn't really matter. It's simple to do. The cluster stays online while you're doing this, and it continues to serve requests while we redistribute the data onto the new shards. And when the new shard is online, it comes online, the operation is complete, and the clients are automatically talking to the new shards. So what we do is we update the Redis topology map so that the clients understand what new IP addresses, et cetera, where the hash slots are, and all that. So remember, when you want to scale write capacity, you should consider adding shards instead of replicas. Now, whether you're using cluster mode enabled or disabled mode, you can also scale your cluster vertically. Now, we do this by, we provision a cluster of the instance size that you ask, whether it's smaller or larger. So let's say in this instance we have a cluster running on R5.x large type instances, and we want to scale up to the R5.2x large. So we're going to provision a new cluster and perform all of the managed services that we spoke about earlier, such as installing the software, configuring it, hardening it, and so on. And now once that new cluster is ready, we start copying that data while the existing cluster continues to serve requests. And once the process has copied all of the data to the new servers, and after they're in sync, we then switch the DNS entry and cluster configuration as well over to the new system. And this process takes about a second on the control plane side, so it's really fast, but it will take a little bit longer from the client perspective because the clients have to disconnect from the old cluster and establish a new connection to the new cluster. And while the DNS entries for the endpoints will remain the same, the IP addresses on the back end are actually going to change. So we want to make sure that we aren't caching DNS data for too long on the client side. Now, most clients by default will attempt to reconnect when a connection drops, but of course you want to make sure to test this before you do it in production, just to make sure that your application handles it well. So let's quickly recap the major differences in scaling approaches here. So with vertical scaling, all instances in the cluster are changed at the same time, right? And with horizontal scaling, we're just scaling individually. So, maybe a shard at a time we're either adding or removing. So it's typically much faster as well. Vertical scaling, because you're changing all the instances at the same time, the cost can have a dramatic impact, whether up or down, based on that. Whereas with horizontal scaling, again, since you are scaling incrementally, you're just paying the difference of adding or removing those shards. And with vertical scaling, it's going to cause all clients to disconnect and reconnect. And horizontal scaling will simply update a topology map, and most client libraries stay connected already. And finally, vertical scaling is supported in both cluster mode and non-cluster mode, whereas with horizontal scaling, it is only supported in cluster mode enabled mode. Okay, to recap scalability, I'd like to quickly call out some of the major points to remember from this section of the session, as well as a few additional pointers here. So first, unless your client library doesn't support it, we encourage you to use a cluster mode enabled cluster for Elasticache for Redis. When you need additional read capacity, we suggest that you scale out by adding read replicas. And when you need additional write capacity, consider adding shards to your cluster. And then we also want to leverage Amazon CloudWatch to monitor Elasticache clusters and then set alarms for different thresholds as well. And when considering these scaling operations, you really should scale before you meet those thresholds or reach capacity. Scaling operations can take longer and could actually compete with your workload if you wait for too long and you're competing for resources. And then finally, we want to use Amazon Simple Notification Services in conjunction with CloudWatch so that you're aware of trends or certain conditions. Now, that's how Amazon Elasticache for Redis handles scaling. And now we're going to move on to a related topic, high availability. I say it's related because Redis actually relies on replication to provide that high availability. So high availability is provided through, specifically through Redis replication built in. If a primary node fails, a read replica node is going to be promoted as the new primary. And how that happens is what we're going to be talking about here. So let's take this typical deployment. Here we're in a 3-region availability zone, or region with 3 availability zones, excuse me. Now we create the cluster, and you can choose which AZ each node is going to go into if you like, or you can let Elasticache choose for you, which is what I would actually suggest if you don't have specific requirements otherwise. And let's see, we have a primary here in zone A, and we have 2 read replicas, one each in zone B and zone C. We can also see that the data is being replicated from the primary node from zone A to its associated replicas in the other zones. Now, if you have a single shard, then all of your data will reside in this shard. But in this example, we're going to have 3 total shards. So each shard is going to have approximately about a third of the hash slots. And hash slots automatically determine where Redis keys will reside in a relatively uniform way. Now, our first shard is responsible for hash slots 0 to 5,454. Now we see our primary node for shard 2 in AZB, and it's responsible for the second set of hash slots. And since this primary is in AZB, which you'll notice is located in an AZ other than the first shard's primary, its read replicas will be in AZA and AZC. And then finally we have the shard 3 primary in AZC, and it's going to be replicating data to its replica nodes in both AZA and AZB. Now, remember here that these primary nodes are the only nodes that you can write data to, but you can read from them as well. In turn, those primary nodes are going to asynchronously replicate their data to their read replica nodes. And read replica nodes are read only. So if you try to connect to these read replica nodes and write to them, delete, update, etc., you're going to receive an error. That's all. So how does this actually work during a primary node failure? Let's say the primary node of maybe shard 2 here experiences a failure. The first thing Elasticache does is it determines which read replica node has the lowest replication lag. And this is actually a metric you can monitor in Amazon CloudWatch. So in this case, it's the replica in AZA. So we're going to take the failed node out of the cluster, And then we're going to promote the replica in availability zone A as the new primary. Now, this change is going to be recorded in the cluster topology map, and it's going to be sent to all the clients. So there's no need to change any DNS entries, configuration, and clients are going to see this immediately if they query for it. Now, the newly promoted primary node is going to start replicating its data to the remaining replica node in AZC to ensure it gets the latest data. Now, when a replacement node is automatically provisioned and ready again to replace the old one, it also starts to receive replication updates from the new primary node as well. And so at this point, we are back to a fully restored cluster with 3 primary nodes with 2 read replicas each. Now, what happens in an availability zone failure? So if we experience the unlikely event of an availability zone failure, a similar process happens to what we just talked about. So let's say we have availability zone C experience a failure. Now, in this situation, it means that the primary for one of the shards and the 2 read replicas for the other 2 shards are no longer available. So at this point, we remove those nodes from the cluster topology map so that clients are aware of the changes. Now, keep in mind, even in AZ failure like this, we still have read access to 100% of our data. And we have 1 read replica in each shard, and in some cases we have 2 read replicas, right? So we also have the ability to write to 2 out of 3 primary nodes. So in this scenario, if we lost that AZ, we can still read 100% of our data, but we've temporarily lost write access to 1 out of 3 primary nodes, at least until 1 is promoted. So like before, we determine which of the 2 replicas from shard 3 has the lowest replication lag, and we promote that as the new primary for that shard. And in this scenario, we're going to promote the replica in zone B. Now, we promote that replica to be the new primary for shard 3, and then it begins to replicate its own data over to zone A's replica. Now, again, we have 100% write coverage in our cluster again. And once zone C comes back online, the associated the associated nodes in availability zone C are then brought into the cluster topology map, and the primary nodes begin to replicate their data back over to zone C. And again, we're back to a fully restored cluster. So a couple of points that we should make here that you should take away regarding high availability. One of the best practices is to deploy at least 2 read replicas per shard. And again, that gives us not only increased read capacity, but also the ability to provide fast failover. We want to spread our primary nodes across multiple availability zones and place those across as many AZs as you can before you start repeating in the same AZ. And we encourage this because really, in the unlikely event, again, of an AZ failure, we want to avoid that condition where multiple primary nodes are going to be unavailable. Related to that point, we want to deploy our read replica nodes in different availability zones from their associated primary node so that we don't risk losing both a primary and a read replica in that situation. And then finally, we want to test our failover feature. We have this feature called failover primary that you can use either in the console or the API, and we'd encourage you to use this feature to see how your application behaves. All right, moving on to security. This is probably the most important part of the session, so I've actually saved it for last. So I'll summarize some best practices towards the end of this section, but most of the remainder of this session is actually going to be focused on Redis's new feature, role-based access control, that we just recently released. So with ElastiCache for Redis version 6, we've introduced a concept of both users and user groups now, and we're going to walk through how these work. So before ElastiCache for Redis version 6, the Redis implementation really only had 2 options when it came to authentication. The first option was to connect to your cluster without any authentication enabled at all. And of course, we would never recommend this, but some customers use this configuration maybe for their personal development environments. The second option was to use what we call a default user, and that was the only user available, with a standard authentication token, which really can just be thought of as a simple password. And so when clients accessed a Redis cluster, and after they successfully authenticated with that authentication token, it had access to essentially all the data inside the cluster. But now with ElastiCache for Redis version 6, we've introduced something called role-based access control. Now we have the ability to create user accounts where each user account has its own password. This means you can create an account maybe for a process that just reads the cache keys. And this account can have, its own password, or you can create one maybe for the marketing team, or maybe one that is responsible for an analytics application that just reads data from Redis. So the point here is that when you provide credentials to authenticate now against Elasticache for Redis, it doesn't have to be shared with anyone else now. So it can be specific to a person, a team, or even a role. Now, if we take those 3 users that we just created, read, cache, marketing, and analytics, and we create user group A, we can assign specific users to this user group. And here we're going to assign the read cache user and the marketing user to user group A. Next, we're going to create user group B. And in this user group, we are going to assign that marketing user, again, to user group B. And we'll also assign the analytics user to user group B as well. So you can tell here that the user can be assigned to multiple user groups. So when we create these or modify an Elasticache for Redis cluster that supports this role-based access control, we can use these user groups against that cluster and have some actions cascade to it. So we're assigning user group A, which contains the read cache and the marketing users to both clusters 1 and 2. And when we do this, it's going to create those users on that cluster. And then you can use those user accounts to connect to any node inside of that cluster, regardless of the node, read-only or primary. Now let's assign user group B to cluster number 3. And so we see that a user group can be applied to one cluster or multiple clusters. We can also tell that one user can be created in multiple user groups, even if it's multiple user groups and assigned to multiple clusters. And then what we can do here is, so let's say we have our marketing user, right? And we need to either, let's say, change the password or even delete that account, doesn't matter. So through the relationship of users to user groups, and then from user groups to clusters, if we change the password or delete that user, what's going to happen is that change is going to cascade through the user groups, and it's going to apply to all the different nodes where that user account is located, again, even if it's in multiple clusters. So that's how we can create users and manage users across clusters with user groups. Now what we'll do is talk about how each of these users is authorized to do specific actions. So let's start with that read cache user first. We want this user to only run the Redis get command, which simply reads a string object, and that's all it does. We don't want this user to run any commands except get, so no set, no list, etc. We also only want this user to have access to cache keys. So we can do that by pattern matching, which I'll show you. Now, we need to define the specific access string for that read cache user. The access string is something we're going to provide to Elasticache that controls whether if the user is enabled, what commands the user is allowed to run, and which keys the user can. This is a string you'll provide to Elasticache through either the AWS CLI or the Elasticache API, or through the console. So in this example, for our read cache user, the first argument is going to be on, which means the user account is enabled. And if we modify an existing user and use the value off, that actually means that existing connections are going to be maintained, but new connections are not going to be allowed. And this is different than, let's say, if you actually removed a user or deleted a user. Any existing connections then will actually be terminated, and that count will be deleted at that point. So the next field in this example is showing the key space that the user is authorized to access. Here we're limiting key access to any key that begins with cache colon. So if a key begins with that pattern, this account is going to have access to it. And next, we are explicitly saying that to begin with, we want to remove all commands from this user. When we list the commands in the access string, a minus means deny and a plus means allow. The @all keyword is actually an alias for all commands, so we don't have to specify all of the commands individually. And there are also categories of commands that you can use here too. And those are all prefixed with the character. So if you see an alias, it means there are really just a bunch of different commands behind it associated with it, and that alias just makes it easier to set up. And then finally, after we've explicitly said no commands are allowed, we then add back in the ability to run the Redis get command. So as you can see with this user, we can see that the user is enabled, has no authority to run any command except get, and only on keys that start with #. Now let's look at two more examples just real briefly. We have a marketing user. Now the marketing user doesn't really need to be limited in the commands that they run, but we want to make sure that they are limited to just any keys that deal with marketing, right? So what we're going to do is we're going to enable the user with on. We're going to give them all commands with the +@all. And then we're going to give it two different pattern matches here that you can see. One is the mktg : *, and then one is marketing : *. And so you can see you can actually add multiple pattern matches in a single line. And then finally, our analytics user. So the analytics user really, let's say it's an application that's focused and it only really needs to read data. It doesn't need to write any data. And it can read, let's say, all the data. So it doesn't really matter, what it is. So it can be anywhere. Now, we want this user to be able to run all the read commands. So we give it the on, which is enabled. We give the ~*. And then what you can see is we do the +@read. And that's kind of a special one, again, because that's an @alias. And so what we're saying here is that this user can run any read command in Redis on any node, essentially, on any key, but they won't be able to do any type of writing or updating regardless of the key, right? And the other thing I want to point out is we didn't explicitly put the -@all or +@all. So what we're actually saying here is we're implying that we only want to have +@read, and we're implicitly saying that we want to deny all others. So Elasticache is actually going to go back in and add a -@all in front of that for us if we go back and look at it. All right, so we're going to look at how these users behave on the command line with Redis CLI, and we'll see a few examples of when they try to access something that they're not allowed to. So here I'm going to be using the Redis 6 version of the Redis CLI, and I'm going to be connecting with the the marketing user, and then I'm going to type in my password, and then I'm going to try to set the marketing : *a to a value of 1, and I get a response because I have permissions to run against the marketing keys. I run get marketing : *a, and so you can see that we ran both a get and a set against the marketing : *a key. And now I want to get another key called cache : *a. So we launch that, and that's actually going to give us an error because remember we restricted the key space to anything with marketing or mktg, and this actually begins with cache : And you can see the highlighted blue text here, and I highlighted it because it's going to be a little bit different than the next example. So in this example, we're going to connect with the read cache user. We're going to type in our password. Excuse me. Then we're going to actually run the get command that just failed from the marketing user, right? So if we run cache or get cache : *a, and we get a successful response, because again, we're authorized for that key space. Now let's set that same key to a different value with the set command. And here we're actually going to get an error. Even though we were able to read it, the read cache user isn't allowed to use the set command. So in this first example, we see an error based on the key space attempting to be accessed, and on the second, it shows an error based on a command trying to be accessed. Now, you're probably starting to see some of the flexibility, right, and some of the power that this new authentication and authorization model provides. It is very, very, very powerful. So in addition to these controls, we have new metrics that are emitted to Amazon CloudWatch that really are going to help you monitor situations with authentication and authorization. So they're divided into three categories. The first, which is here's authentication failures. And those are going to occur when a user attempts to log in without the appropriate credentials. We also have key authorization failures. That's the second one. So like you saw a moment ago, what happens is it's when a user attempts to access keys without the appropriate permission. And then the third is going to be command authorization failures. Again, as you saw just a minute ago on the last slide, so where a user attempted to run a command without authorization for that specific command. So these metrics are emitted to Amazon CloudWatch every 60 seconds. And you can view these metrics in any way you want, multiple types of graphs, whichever works best for you. And so now not only do you have better control over access to your Elasticache Redis clusters, You also have the ability to view metrics related to that access, right? And since you are using Amazon CloudWatch for these metrics, that means you can actually set up notifications for them as well, which is pretty nice. You can see here that I'm in the CloudWatch screen, and in the lower right-hand corner, if I clicked on these alarm bell icons, I can actually configure an alarm based on these metrics. And I can also set up simple notification service so that I can be notified of any incidents as well. Now, if we need additional details on one of these authentication or authorization failures, what we can do is connect to Redis directly on the cluster through the Redis CLI. And what we can do is run what's called the ACL log command to find out a little bit more about this. So here what I'm doing is typing ACL log, and I've highlighted a few lines of output here. So you can see that this user tried to run the set command, and they were connected from a specific IP address and a bunch of other useful information. So very powerful. Now, let's summarize what we learned about security, along with a few points that we really didn't have time to dive very deep into. So first, security of the cloud is critically important here at AWS. By default, we don't ever expose your Elasticache clusters to the internet. We also encourage you to use encryption in transit and encryption at rest with your Elasticache for Redis clusters. You should also test the performance impact by using these with a kind of a production-like workload so that you understand that before you put it into production. Of course, the role-based access control that we introduced recently, that's a very powerful feature and very flexible. And we would encourage you to use it, especially in situations when maybe different applications or different customer data might reside on the same cluster. And you'll also want to implement a very specific key naming pattern to account for that as well. Now, since Elasticache resides within your VPC, you also have the benefit of modifying your security groups, which can control ingress and egress rules. And because Elasticache for Redis sends those authentication and authorization failures to Amazon CloudWatch, we would strongly encourage you to use that functionality to then set up notifications with Amazon simple notification services so that you are alerted of these failures. And then last but not least, we would always encourage you to stay current on your version of Redis so that you can benefit from multiple things like improvements in performance and scalability and security. So a few resources before we go. So many of our customers' questions and answers are listed in our FAQ. They're at this link here. If we release a new blog, you can find it on our Elasticache specific blog, where we cover really a wide range of topics, anywhere from right sizing, best practices to monitoring to even examples of code. We have our customer forum. It's really a great place to ask questions, engage with our community, and watch for product feature releases. And then we have a page that's dedicated to helping you get started with Elasticache for Redis. Now, before I close, I'd like to say that if you enjoyed this session or just really want to learn more about Elasticache, you can view these two sessions. If you weren't able to, you should be able to go back and watch them again. They're very deep, very technical, and some of the senior colleagues I have here are delivering them. So let me say that I'm, again, just delighted that you decided to spend time with me and all of us here at AWS for reInvent this year. And if you have additional questions, please reach out. Don't hesitate. We're happy to help. And I'd also like to ask you to fill out the survey, and for this session specifically, so that we know what we can improve on, what we need to change, and maybe even what you liked. So I hope you have a wonderful rest of your day and that you enjoy the rest of your time here at reInvent. Thank you.